So I welcome you for the this NPTEL discussion session. I can see a student there. Hi Gaurav, how are you?
Hello,
Hi,
I'm fine. How are you, Nikhil sir?
fine, fine. So how is the course going on?
It's going on, but this week five course is still it's going off the head. Actually,
Okay. In
that is a
this,
bit
I
hard
think
to understand.
some Timoshenko beam theory is covered in this thing.
Yes, yes, yes,
Okay,
yes.
okay. Hold on, you will see same things. You get to if you don't get try to go through the videos again.
Hmm.
You will get it. How are the assignments going on?
Assignment till now it's fine. Means week five I have not started yet.
Okay, okay,
Till week four it's going good.
okay.
Yes.
Okay. So one more student is here. So let's start today's class. This is week five of FEM course. I am Nikhil Gupta. I'm a research scholar in Department of Civil Engineering in ISC Bangalore. So what today I'll do, I'll cover the assignment four solutions. I'll solve, give you the detailed solution of each of the problem, and then some of the problems for which will be helpful for solving the questions in assignment number five. So I'll start with the question number one. What it says: consider the following propped cantilever beam length 2L, okay, which is loaded in UDL for half of its span. Okay, it's shown here, and we have to answer the 1 to 3 questions. The beam is discretized with two elements of equal length, and beam have a constant EI throughout. That's good. The nodes and corresponding degree of freedoms are shown in the figure of the beam. Solve the beam for unknown generalized displacement of the applied load. So this is a basic FEM problem from starting from the beginning, discretizing it and putting the nodes. You have to solve it, the unknown displacement for it. So the question which is at unknown generalized displacement of the beam degree are 3, 4, 5. What are they? This is unknown, this is unknown, and this is unknown. Rest displacement, you know that u1 is 0, you know theta 2 is equal to 0, and u5 is 0. This one. Okay. So final equilibrium equation you have to find out to with the known forces. So you see this is the reduced stiffness matrix which is shown as Ku is equal to F. You have to solve the problem. Let's start solving it. This is a beam. Loading is given like this. So I'll make it. This is 1. This is 2. This is 3. This is 4. This is 5. And this is 6. So this is element number 1. This is element number 2. Now full is 2L. So this will be L and this will be L. Okay. So when we start solving this, what we know if we have a beam like this, and if 1, 2, 3, 4 are the degree of freedoms, we know for that element K element, we know the stiffness matrix, which is the elemental stiffness matrix, which is Le cube. This is 6 minus 3 Le minus 6 minus 3 Le minus 3 Le 2 Le square 3 Le square minus 6 3 Le 6 3 Le. minus 3Le minus Le square. Oh, it should be plus only. Le square, then 3Le, and here it is 2Le square. So since it is written for one of the element, so this is 1 2 3 4 the degree of freedoms, and similarly 1 2 3 4 are the degree of freedom for this elemental stiffness matrix. Similarly, we know that for this beam, the force vector, what it is, force of an elemental vector is q naught Le by 12 6 minus Le 6 Le. All this k elemental and f element is covered in your theoretical part, so I am writing it directly. For this also, the degree of freedom will be 1 2 3 and 4. Now what you know that full beam has E and I constant. Elemental 1 has L1 or L, not L1, so it is L. Also L of element 2 is also L. Both are having L length beam. Okay, so now we'll put this L into the main matrix as L equivalent. So we'll get, we'll get K elemental of 1 as 6 minus 3L minus 6 minus 3L minus 3L 2L square 3L L square, then minus 6 3L 6 3L minus 3L L square 3L 2L square, and outside same thing will come, which is 2EI by L cube. I've just put L equivalent as L. So for this it will be 1 2 3 4 1 2 3 4. This is for this element we have written the K matrix. Similarly, we will write for K2 as well. So what K element 2 will be? It will be, again, since length is same, the matrix values will remain constant, same as the previous one. So we can directly write it. So the thing which will change is the degree of freedoms. You see in the next beam, the degree of freedom are 3 4 5 6. So here it will come as 3 4 5 6 and 3 4 5 6. Okay, so you have written the elemental masters of the both the element. Now what we have to do, we have to make a global stiffness matrix. So k global will be, so the outside term is still same, 2EI by L cube. Now how many degree of freedoms? Now we have 1 2 3 4 5 6 in the full beam. To admit two people. Oh. Okay, so now we'll write here 1 2 3 4 5 6. Okay, so when we'll combine this, we see 1 1 is in this one, so it will be 6 here. Similarly, minus 3L, due to this 2 in 1, then it will be minus 6 3L 0 0. Then in the second one, it will be minus 3L 2L 3L L square 0 0, then minus 6 3L, 6 plus 6 here it will come, so it will become 12, then it will be 0 and minus 6 minus 3L, then 0 0. So this is the fourth column, so fourth column will be minus 3L, L square 0, 4L square 3L, L square 0 0, minus 6 3L, 6 3L, 0 0, minus 3L, L square 3L and 2L square. Okay, so is there anyone who has a doubt how this global matrix has been formed? I have directly written the solution. If anyone is having a doubt, I can go in detail and explain this how it is formed. You can, if you want, I can zoom in and you can see. I'll wait for 2 more minutes so that you can grasp it how it has come. It's just I am adding the known degree of freedom, and if they coincides, these that terms are being added or subtracted, whatever means according to the sign it has been done. So I hope all this till now is clear how to form a global stiffness matrix. Now, as we have made a global stiffness matrix, we also have to find the force vector for each of the element. Let's say we are making it for this first element. So what we have written here, it was q le by 12, so we'll put the le value as L, so it will come q naught L by 12, then it will come as 6 minus L, 6L. So for, since it is for element 1, so degree of freedom will be 1 2 3 4. Similarly, if you put F2, since the L is same, so it will also become the same quantity in the vector. So it is 6 minus S, 6 and L, but the degree of freedom will be changed and will become 3 4 5 6. Now what we see in element number 2, which is this, we see there is no loading acting, so q naught is nowhere, so this q naught will become 0 and this full will be 0. So, or we can write in a vector form as well, it is 0 0 0 0. Okay, now we see we can find the reaction also. So q element of 1, let's say I1, so what it will be, we'll define it as q1 1, then q2 1, q3 1, q4 1. Similarly for second, it will be q 3 2, q4 2, q5 2 and q6 2. The top 1 and 2 are for the element, and the bottom 1 2 3 4 and 3 4 5 6 are for degree of freedom in front of what it is denoting. So see, now what we have found out, we have K found at K matrix, which is global, and we have a we have U and we have full F. Now this F consists of force vector plus the reaction vector. So if you find it both, so this F vector with this will be due to loading, this will be reaction. So if you find the F global, which is q naught L by 12, and the same thing as 6 minus L, 6L 0 0. Now it is covering for the global time, which is 1, 2, 3, 4, 4, 5, 6. So full degree of freedoms means we can say this is a global force vector for this beam. And for Q, now Q will be full Q1. Now we can see one more thing, the reaction, what are the reaction which are acting, then we can write this. So we can reduce this and we can write the beam which is like this. So no, so this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So we know this, that for a load vector we have to see where the reaction are acting. So q3 is equal to 0, q4 equals to 0, and also q6 is equal to 0, because these are not the reactions which are acting with, we have to compute it. So to solve it, now what we have our full K matrix. We have u1, u2, u3, u4, u5, and u6. Then we have q1, q2, then q3, q4 are 0, q5 will we have, q6 is 0, plus the q0 L by 12, this is the force vector which we have computed, 6 minus L, 6L double 0. Okay, now I think you know how to solve it. Means if we have this K matrix and this U matrix, we make this as U as unknown, this U unknown, U known, then F known, F unknown, and we used to solve the bottom one first where we know U, and then we compute this and we solve the top one. So let's start solving this problem. So we have 2EI by L cube, which is 6 minus 3L minus 6 minus 3L 0 0 minus 3L 2L 3L L square 0 0, then minus 6, this is 3L, then 12, 0 minus 6 minus 3L, and minus 3L L square 0, 4L square, then 3L L square 0 0, then 0 0 here, minus 6 minus 3L 3L L square 6 3L, then 3L and 2L square. Okay, this is the K matrix we have computed. Then u1, u2, u3, u4, u5, and u6. Now we know from this problem that u1, u2, and u5 are 0. u1 0, u2 0, u5 are 0. Okay, and in the RHS it will be q0 L by 12, 6 minus L, 6L 0 0, plus q1, q2 0 0, q5 and 0. Okay, this is the full ku is equal to f we have written. Now we know that these three are 0.
I have a question here.
Yeah, tell me.
Is it okay? Yeah, my question is why that Q1, Q2, and Q6 are not 0?
q1, q2 and q5.
Q6.
q6, see, q
Yeah,
these q1 q.
load factor.
Okay,
Because we don't have any point loads, right? Basically, that represent point loads, right?
no, these are the reaction forces.
Okay, reaction force.
reaction forces. So Q1
Reaction are applied also, right? Even if there is applied load also, we will just
applied
apply.
load we are calculating in this F.
Yeah, that there we calculate the UDL,
UDL, yes.
right? If I have a point load, then
Point load, I have one more question we'll discuss there. Yeah, I have a question. You have to integrate in terms of direct delta function. I'll
okay.
show you. I think I have this time.
Now my question is, when we have both UDL plus point load,
Okay,
how we going to do
you'll
that?
see this question.
Yeah.
I'll cover in this.
Okay.
This. So UDL you have covered here. Now this Q are the reactions. So now you are calculating it. So to solve it, what we'll do, we'll make it, this is a full K matrix. So we have to make it a reduced stiffness matrix. So you will get it as 2EI by L cube, then 12, 0, minus 3L, 0, 4L square, then L square, minus 3L, L square, and 2L square. This is U3, U4, and U6 equals to Q0 L by 12 and 6L0. Rest QR 0 for this reduced matrix. So now you see the question, what is the options which are given. So okay, they are asking the reduced stiffness matrix only. So if you compare the first one, it is 6L0 Q0 L by 12. I think we have got the same thing here, 6L by 12, and the matrix is same. So I think yes, the answer is AA. This 12 is there, minus 3L, this same matrix we have got, and the RH is also same. 6L. Okay. So answer is A. Let's go to question number 2 now. So it's the connected question. You have to find out which would be the global force vector. So I think we have computed in this problem itself. So Q global is this, it is Q0 L by 12 along with 6 minus L, then Q1, Q2, and Q5. So the option is D part. If you see, it is same Q1, Q2, and Q5. So we have already computed this in previous question. So question number 3, what will be the unknown generalized displacement vector if L is equal to 1 unit and Q0 is equal to 12 unit? So it is the continuation of the first question. Now they are telling to solve this problem. So I'll write this equation again to solve it. This is 2EI by L cube 12, 0, minus 3L, 0, 4L square, L square, minus 3L, L square, 2L square, then U3, U4, and U6 along with I'll write here Q0 L by 12, 6L0. Solve this problem, it's just the AX is equal to B problem. So for that you have to compute A inverse B and you will get the X or U values. So so if you will see, this is U3, U4, U6 with A inverse of B. So here A is 2EI. So now we can see the L is 1 and Q0 is 12. So we can put the values as well. So L will be 1. If we put, it will give you the value like this: 0, 4, 1, minus 3, 1, 2. So when you find the inverse of it, either use MATLAB or hand computation is also okay for 3 cross 3 matrix. You will get this matrix. I have already computed it. Okay, so this I have done. For this B vector is 6, L and 0. So when you multiply by A inverse B, you will directly get the U, and the solution will be U3, U4, U6. It's just the computation. You will get is 1 by EI. So then will be 0.4062 minus 0.0312 and 0.625. So this is the answer you will get, and the answer is C part. Yes, correct, C part. So let's go to another question. This is question number 4. Now what we have to do, we have to find the unknown support reactions. Means moment at joint A and reaction at C with L is equal to 1 and Q naught as 12 points. So if you see, while solving this problem, we can directly say what will be the reactions. We can use this equation. So after using this equation, we can directly write R1 equals to Q naught L by 2 plus Q1. R2 is equal to minus Q naught L square by 12 plus Q2. Q3 as Q naught L by 2, I think, plus Q3. R4 as Q naught L square by 12 plus Q4. R5 as 0 plus Q5. R6 as 0 plus Q6. So we have shown that Q3 is 0, Q4 is 0 and Q6 is 0. So this, when you put the values of L and Q naught, what we'll get is 6 plus Q1, then minus 1 plus Q2, then 6, then 1, then Q5 and 0. This is the force vector we have got. Now as you have solved the previous problem, you can put these U values in the global stiffness matrix in this problem, and you can get the values of these reactions as well. So once you solve it and substitute and solve the values, you will get the answer as A part. It's just the manipulating and putting the substituting and getting the values. Okay, so this is now question number 5. This is a bit different from the first question. This is not the continuation. Let's read the question first. Okay, it says identify the incorrect statement corresponding to a two-node beam element with cubic Hermite interpolating polynomial. Okay, the element is shown below as indicated. The degree of freedom are indicated between 0 to L, and phi are the safe functions. Okay, and we have to find the incorrect statement. So do you know the difference between the Hermite interpolating function and the Lagrangian interpolating function? Anyone who can tell what is the difference between the Lagrangian interpolating function and the Hermite interpolating function or the polynomial? Okay, anyone heard of Lagrangian polynomial or Lagrangian interpolating function? Okay, no problem. When we write a Lagrangian interpolating function, we are dealing with u1, u2. But when we write Hermite interpolating function, along with u1, we deal with theta 1 as well, u2, theta 2 as well. So this is the basic difference. Now let's get back to the question. What is it is asking? So it is asking what is the incorrect statement. Okay, so what they had defined, they are defining the n1 n2 are in terms of I. So let's see how it behaves. So this is the beam, this is 1, this is 2, this is 3, this is 4. Now I have to plot n1 in this. Can anyone tell me what will the graph of n1? How n1 will behave? So what are the properties of shape functions? There are two, three properties which shape function should follow. This is node number 1, this is node number 3, node number 2 only, or no, node number 3. So can anyone tell me the properties which shape function have? Okay, tell me what will be the value of n1 at node 1? Okay,
Should
no
be
problem.
1.
It will be 1, yeah. So it will be 1, but when we increase this, can't you see that in 2 also it has increased to 1? The shape functions has a property that at that node the value of shape function will be 1, at all other nodes it will be 0. Now if I
Yes.
increase this one, n1 at 1 as 1 unit, then isn't not that in node number 2 also has a n1 value as 1? Can anyone think why is it happening and how to rectify? So by making this point value as 1, you have to make node 2 n1 value as 0. So there is a catch in this, that this 2 degree of freedom is a slope. This is not a displacement. So for making the shape function, it should go like this. Now you see what happened. N1 is having at 1, it is having a 1. But 2, since it is a slope, you see the slope is 0. So 2 also it is 0. For 3 also, since it is not going up, it is 0. For 4 also, the slope is like this, so it is 0. Similarly, if you make it for 3, it will go like this. Is it clear with everyone? I'll wait if you don't have, means if you have any problem or still thinking about it, what is I have done. Okay, so I think you have understood. Now, can anyone volunteer and tell me what will the shape of N2?
So, at n2 there will be one unit of rotation.
One, correct. So this will be a rotation and it will go like
At
this.
other points, it's
Is
be
0. So
0.
now you see, and 1 it is 0, 2 it is 1, and 3 it is 0, 4 it is 0. So it's correct. And similarly, if you make it for this, it will go like this. So this is for n4. Now you have figure it out. Now let's write according the question what it says. It says it is saying how the this says function depend. So let's write the displacement as phi 1 v1 plus phi 2 theta 2 plus phi 3 v2 plus phi 4 phi 4 theta 2. This is one. Okay. Now since we know by this that phi 1 x plus we know phi 1 x at x is equal to 0 is equal to 1 according to this. Then phi 3x at x is equal to, it is L or 1. The length is L. So at x is equal to L equals to 1. Understood what I have written? I just written the boundary conditions according to the n1 and n3. Here n1 and in question n1 is phi 1 and phi 2. I hope you got it. Now you know this slope is 0 at x is equal to 0. So what you will write? You can write minus of also what you can write now let's focus on these two only. We can write phi 1x plus phi 2x equals to 1, because whenever this is 0 this will be 1, and whenever this will be 1 this will be 0, and similar trend it will happen and it will give a constant curve of 1. So one of this condition is satisfied. So if you see, is there for nex this is okay. So we have to find the incorrect one. Now let's focus on the slope one. So we see del phi 2 by del x at x is equal to 0 is equal to 1, and minus of del phi 4 del x at x is equal to L is equal to 1. It is based on these two. So similarly, if you write, you can write combining this, that del phi 2 by del x of any x plus del phi 4 by del x at any x equals to 1. So this is also satisfied. So you see del phi 2 is 0 at x is equal to 0, and phi y 1. Not required to get this full equation, but okay. So you have to find the incorrect statement. So this cannot be verified. Since 2 are displacement, 2 are theta based, so this can't be verified in this, and it can be said this is the incorrect statement. Okay, so question number 6. Though this is a good question. Let's read it. So 4 cantilever beam ABCD are loaded with point load. UDL is there, triangular load is there, parabolic load is there. All the beams are described with 3 node single element. Displacement of Euler-Bernoulli beam cannot be captured exactly by considering this which element. Okay. So can anyone think about this question? How to start this question? What to write?
Yes, from how I solved it was for 300 element, there would be the displacement will depend upon the fifth degree, means x to the power 5.
Correct.
Okay,
Uh,
so and for the first question, that is
mhm,
simple cantilever with point load,
mhm.
we know the deflection is third, means PL
Correct.
cubed by 3a, so
Mm.
3 degrees, so it will be
Uh,
solved.
correct.
It's
It's
in
correct. I
similar
understood. You
approach,
are
it
no.
was solved.
Good. So what Gaurav said, I'll tell you. So we have to find the how much order of deflection is present in the beam. Means order of deflection of beam. So we all know we can define moment as EI d2y by dx square. Now if you will get the this okay, so when you make a bending moment diagram in this question, it will be like this. This is 1 degree. When you make a diagram in this, it will be 2 degree. In this, it will be 3 degree, and for this it will be 4 degree curve. So for if we go by this problem, if your moment is 4 degree, when you integrate this, it will go to 6 degree. So you require a 6 degree of freedom equation to solve this. Now what question is saying? The question is saying that this for 3 node single element. So for the 3 node single element, what you can assume is y is c naught c1x plus c2x square plus c3x cube plus c4x power 4 plus c5x power 5. So 3 node elements, so you have 6 degree of freedoms. So you will have 6 unknowns. So the maximum degree here is 5. So since in this part you require 6 degree of freedoms equation, so beam D can't be solved by this. Since degree is max degree, no max degree, order is greater. Order of deflection in beam D is greater than maximum degree. So answer is D part. Okay, so let's go to question number 7. This is the same I have solved in the last class as well. Let's solve this now. Okay, so in order to find the natural frequency, elemental mass and stiffness matrix are calculated and assembled to global mass and stiffness. Okay, now whole system of equation are partitioned corresponding to unknown degree of freedom. Okay, the unknown generalized 4 5 6. Okay, I think I don't know if the question has the figure or not in the assignment, but it is like this, where this is 2, this is 1, this is 3, this is 4, this is 5, and this is 6. Do you have the this beam made in your assignment? Because in assignment I didn't find this beam related
No,
to.
no, in the assignment there is no picture. We
So
have to just visualize it.
you
We
just
have to assume that it's like
it's the
this.
same beam in the question number 1. Something
Okay.
is changed. You just have to visualize it because their support reaction is also changed. I think they missed to draw the diagram there. No problem. So let's go with the question. So boundary condition, what it says is fixed end A. The displacement will be 0. Along with it, slope will also be 0. It is as x is equal to 0. At x is equal to L, the moments and shear force will be 0. Okay. So since it is a beam, we have solved it for global stiffness matrix. I'll write the same we have found in question number 1 and don't waste time in solving again. So the equation which we got was this. Okay, so this was the K global matrix. Now we also know that mass stiffness matrix, where M is equal to rho element, E
awan
element.
ya awan ba ano ke ba
So He is equal to L.
hmm 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 hmm
Okay. So this ME of an element will be MHE by 420, then 156 minus 22 HE, and 54, 13 HE, 4 HE square minus 13 HE minus 3 HE square, 22 HE, 156, 4 HE square. So this is the general mass stiffness matrix which you get in the by solving this equation, and it is covered in your theory class. So now I'll write it for first element. For that, He is equal to L. So it will be, I'll replace all He with L. We'll get this matrix. So 1, 2, 3, 4. 1, 2, 3, 4. Similarly for ME for second element, since L is same, properties is same, so the matrix will also be same. So it will be 3, 4, 5, 6, 3, 4, 5, 6, because M2 is related to second element. So degree of freedoms are 3, 2, 4, 3, 4, 5, 6. Now according to this, you will form a mass global matrix which will be ML by 420. You will add the corresponding if present. Okay, so this will be symmetric. I'm not writing here. So corresponding degree of freedom 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, you got this also. Now we have to see the load vector as well. So for free vibration, no load vector. This we have studied in the class. So for given loading, Q vector will be, so don't think any loading is given or not. So Q will go as 0, 0, 0, 0, 0, 0 plus the reactions Q1, Q2, Q3, Q4, Q5 and Q6. So here Q1, Q2 and Q3 are the unknowns. Rest Q4 is 0, Q5 is 0, Q6 is 0. So To solve it, we have to do k omega square m of u is equal to f, or this is also f. So let's see how the results are coming. Okay, so it is saying us to get the reduced stiffness matrix. So the deflection are u4, u5 and u6. When you write this matrix, what you will get here? Okay, so you have u4, u5 and u6. So you can remove u4, you can get this matrix. From here you can get k matrix, also you can get this matrix. I think something will be out as well, so it will be 2ei by l cube as well. So if you see the solution, I think the answer is A. So this we are getting it once we match the mass matrix as well. So it is 8L. Yes, correct. So answer is A. Did you get it? Anyone have a problem with this? I didn't write the KU is equal to F again. It's a too big matrix. I just shown how you can get from this. Okay, let's go to other question. What will be the elemental mass matrix? So this also we have computed before. So this is the elemental mass matrix. So it's 156 ml by 420. So m you know is row A. So answer you see this is matching. 54 minus 13, minus 13 it should be minus 13. Yes, correct. Oh. So answer is D. Now okay, now I'll solve this because last time I didn't solve this. So I'll start this solving. Okay, so I'll take the help of this solution and write the full equation what we have got. So the equation what we have got is 2ei by l cube with 4l square 3l l square 3l 6 3l l square 3l 2l square, which goes minus of omega square ml by 420, then 8l square minus 13l minus 3l square 156 22l and 4l square. This is k minus omega m. In again it will be u1 u4 u5 u6 along with it is 0. We have to make a bracket as well here. So if we put the values of L and Q, no, we can reduce a little bit. Let's do it first. 4L square 3L L square, then 3L 6 3L L square 3L 2L square with minus of omega square ml power 4 upon 840 ei, then 8l square minus 13l minus 3l square 156 then 22l and 4l square with u4 u5 and u6 equals to 0. So why I have done this, because in question it is giving like this, so you have to replace this term with 5. So I have made this term here. Now we can write it as putting L is 1, so it will be 4 3 1 3 6 3 1 3 2 minus we can write it as 5, and it will be 8 minus 13 minus 3 156 22 and 4. And to write to full, this will be your equation. Okay, Now we have to here full bracket will put, then u4 u5 u6 equals to 0. Now we have to take the use the eigenvalue problem and solve it. So this is 4 minus 8 5, 3 plus 13 5, 1 plus 3 5, 3 plus 13 5, 6 minus 156 5, 3 minus 22 5, 1 plus 3 5, 3 minus 22 5, and 2 minus 4 5. So we have just added it, and what we'll do, we'll not put the bracket now, we have to get the determinant of it as 0. So when you solve this, you will get, no, you don't have to solve it actually. This is the answer. Answer is C. Okay, so let's, is it understanding to everyone what I am doing? Is it are you getting it, everyone? Okay, I'll
Yeah, I
move
can get
forward. So in question number 10, they are showing unknown force vector component. Okay, so
no.
that's simple. You know that it's Q1, Q2, and Q3. So answer is D.
Yeah, but in assignment we don't have that
You don't
provided.
the what you don't have?
No, we don't have the image.
Image you don't have. I also saw that. So the question is based on this this image. I don't know. I think they have missed the image. Let's see what they do. So it depends on this. Okay. So I have covered the question number assignment 4 questions. Now I have some questions related to week 5, and that will help you in solving the question assignment 5 also. So let's start this question. Question number 1, you can write. So consider the following Timoshenko beam and answer the linked question to 9 to 10. The beam has a square cross section and Poisson ratio as 0.3 with constant EI. The beam is discretized with two elements of equal length. Each element of beam has two nodes and reduced integrand technique is used. The nodes and corresponding degrees of freedom are shown in the figure. Analyze the beam for unknown generalized displacement. Okay, so first I'll tell you how to distribute this load. One of you have asked in this class also before, and I have this problem, so I'll discuss here. So let's say you have this U as UN1 U1 and 2 U2. So or generalize you can write it as UN is equal to NIUI. I'll take a little water. Okay, so now you know this is the we assumed the function of u. Now if you have to find f, what you do, you from x1 to x2 ni q dx. This is the general formula for finding the force vector. So if since here two nodes are there, so your Fy will become x1 to x2, where n1 and 2 is the vector and q dx. So what q here is, q you have to write it as p delta x minus l by 2. I'll to make it more clear, I'll show in the previous page as well. So what this p is doing, I'll make it here. This is the acting load P. Let's say it is acting at L by 2. So this Q can be written as P delta of x minus L by 2. Do you know about this delta function? So what delta function do, whenever you are saying, if you are saying delta x, so this means at x is equal to 0, it is infinite. Rest it is 0. if you are saying delta x minus L by 2, this means this function is at L by 2 is having an infinite value, this is 0. So if you see what this function is denoting, I am saying as it as q is equal to p delta x minus L by 2. It is saying since we are integrating from x1 to x2, so it is saying from x1 to x2 all of the where it is 0, it's still, but at L by 2 it is reaching a 1 value. Oh sorry, I to put it as infinite, it will be 1. So 1, it will be 1 and it will multiply by p, you will get a p value. So it is same applying a load as like this. So it's just a representation of a point load acting at a point. So when we were solving it, we get this x1, x2, n1, n2, p delta x minus L by 2. Till now, is it clear with everyone? The person who asked the question, is it clear? Till now?
Yeah.
Okay. So this is the, so we know for 2 degree, 2 nodes, what are n1 and n2. So these are 1 minus x by L and this is x by L. So we write this p delta x minus L by 2 dx. One more property of this delta is that when you use, this is the property, if you are writing fx delta x minus a dx, you don't need to integrate it directly, you can write this. So if you are integrating fx into delta x minus a, you can directly substitute x is equal to a and that will be your solution. So while solving this, what integration you will get? You will get one integration at 0 to L p 1 minus x by L of delta x minus L by 2 dx. Another will be 0 to L p x by L delta of x minus L by 2. So without solving, you can write it f as p 1 minus L by 2 by L and p L by 2 by L. So it will become p by 2 and p by 2. Since it was acting on the L by 2 section, you are getting in p by 2 and p by 2 on both nodes. If it had been at some other distance, you will get the different values for both of the nodes. So for solving this question, we'll use this. So let's start solving the question. What it says. No, okay, what we have to find it. We have to analyze the beam. Okay. Now what we have to do. So this is a Timoshenko beam. So I don't go deep how the K matrix of Timoshenko beam is computed. That will be covered in the class. I'll directly write the equation. So this will be 4 minus 2L minus 4 minus 2L L square plus alpha 2L L square minus alpha 4 2L L square plus alpha. So this is 1 2 3 4 and 1 2 3 4. Okay, for element 1 this is, for element 2 the values will be same, 4L and 4 minus 2L minus 4 minus 2L L square plus alpha 2L L square minus alpha 4 2L L square plus alpha, which will be 3 4 5 6 3 4 5 6. Okay, so after this you have to write the global stiffness matrix. K G will be G A Ks by 4L it will be 4, then minus 12, then minus 4, minus 12, L square plus alpha, 12, L square minus alpha, then this will be 8, this will be 0, minus 4, minus 12, then this will be 2L square plus 2 alpha, then 12, L square minus alpha, and 4, 12, and L square plus alpha. This will be 0, 0, 0, 0. So 1, 2, 3, 5, 6, 1, 2, 3, 4, 5, 6. Same method I have used as I have solved for the Euler-Bernoulli beam, just the values are different. So if you write it, now you have to see the beam how it looks like. So now you see this u5 is 0, no, u5 is 0, u3 is 0, u1 is 0, and u2 is 0. So we are left with u4 and u5. I think u6, sorry, u6, u4 and u6 are remaining. So we'll reduce this matrix into this u4 and u6, and when we'll form this, what we'll get? We have reduced stiffness matrix will be G A K S by 4L, then it will be twice of L square plus alpha, L square minus alpha, L square minus alpha, L square plus alpha. Okay, so here it will be 4, here it will be 6, here it will be 4, here it will be 6. Similarly, we have calculated the force vector as well. So F1 will be P by 2 0, P by 2 0, plus Q1 1, Q2 1, Q3 1, and Q4 1. This is for element 1. For element 2, it will be 0 0 0 0, then Q1 2, Q2 2, Q3 2, Q4 2. So is it okay till now with everyone? I have not done anything new. Same thing which was I was doing in the first two problems, I have started here. That's why I have done it in a quick way. I hope it is clear with everyone. So when you form we'll assemble the force vector, what we'll get? Q1 dash means Q1 1, Q2 1, Q3 1 plus Q1 2, Q4 1 plus Q2 2, then Q3 2 and Q4 2. And you do this, you'll get, you know that this Q4 1 is 0 and this is 0. Plus we can write P by 2 0, P by 2 0 0 0. Okay. So if you see the problem, a moment is given here. So you know that Q6 is Q6 is M. Okay, should be Q6 or Q4. Okay, sorry. So this is not 0 actually. This is equal to M. It is given. So when you solve it, you will get GA KS by 4L with 2 L square plus alpha, L square minus alpha, L square minus alpha, L square plus alpha U4 U6 equals to 0 and M. So this is the same way. Now you can directly uh, calculate this and you can get the value. Let me see how they have computed the what they want. I think the question is asking this only. Oh, I have done it. The question is far again. Okay, so they are asking this. Identify the correct equation. So I think the answer is one of it. 0m g4 g6 2l square by plus alpha. This is this l square minus alpha. This is this.
Uh,
This. I think the answer is D.
Same issue here as well for week 5. They have not provided
Uh-huh.
any.
So yeah,
In-
that's why I have taken this question.
okay.
I have seen that again in assignment number 5. This image is not there. So I was going to give you the hint about this. So it is that's why I chose this question so that you don't have a problem in solving in question number 5. Question assignment number 5. I just checked yesterday that this is like that. So it will be helpful while solving the assignment 5. Do refer this image which I have shown here. You can see the YouTube video which I'll upload. Pause it and you can get the question image. So I think now I have solved it. One more question I have regarding this, but since this is in the assignment number 5, I won't go to the solution of this, but I will leave it to you. Why I put this question is just because of this image which is missing in the assignment number 5. So that's all I have for today. I hope you will be this image will be helpful for solving the assignment 5 which is missing. Anything else which is anyone having a doubt regarding the concept or theoretical part, you can still ask me. If not today, I'll in the lecture also, if you have a problem, you can ask and later I can discuss in the next class.
Yes, in the lecture, I have some doubts regarding this reduced integration technique.
Okay, tell
How
me.
it was been done.
Reduced integration means the 2.3 point Gauss quadrature.
Means I don't know. Means it's not taught in the lecture yet.
Uh,
But the faculty member was saying that it will be taught later.
uh,
But he was using the reduced integration technique in the
okay.
think the week 5 lectures.
Okay,
Yes.
I think reduced indication I can discuss right away here only.
Yes. Yes.
Right. Discuss. I have it.
There was two technique. One was component integration,
Component
something like
matching.
that. Yeah, component integration, something like that. And
Uh,
second was reduced integration technique.
okay.
With these two techniques, he was deriving the stiffness
So
matrix for
solving the integration.
using. Yes,
Uh, so was it the Gauss quadrature?
he was saying something like that also. It means Gauss quadrature, numerical integration, and all. He
Okay.
said it will be taught later
Uh,
in the later videos, but
uh,
he was using the just writing the equation and solving it right away.
okay,
So
so I'll give you the gist of the Gauss quadrature method.
mm. This is how he derived the stiffness matrix actually. So
Actually, what happens na? To get the stiffness matrix, you get a integration like this: P transpose A E B dx. You get like this? Do you get this?
no,
Uh,
means he has written the whole equation not in this form. Yes,
uh,
so
but
but I remember this in matrix method of structural analysis.
so
It was not like that.
every K matrix, if you get assume U and this is the strain matrix, you can
Mm.
get by this integration. Now, since this
Yes.
integration is too big, you can't do it by any integration method. You have to take the help of numerical methods.
Hmm.
Now, the previously studied numerical methods you have studied, like that Simpson method, trapezoidal method, that can also be
Hmm.
used. But one other gauss quadrature method is another numerical method which is proved to be giving better results than other results than other methods. So what you will do in that, if let's say your integration is like this, phi. Okay, so directly what you can write this integration as w1 phi 1 plus w2 phi 2, so on till wn phi n. You don't have to think what function it is. You just put phi. You can get this value. Now how this w1 w2 wn are depending, I'll tell you that. So it depends on the w's are the weight functions, weights, and phi 1
Hmm.
phi 2 are the value of functions at sample points. So in question you will be told that you have to use one sample point, two sample points, or three sample points. Accordingly you
Hmm.
have to write it. Let's see, you are solving a linear polynomial. So your phi will be a plus b epsilon xi. So now if you integrate it, you will get minus 1 to 1 a plus b xi d xi this. Now let's integrate it directly because it is a simple time you can integrate
Hmm.
it directly. And what you will get a plus you will get a xi plus b xi square by 2, and you will do minus 1 to 1. When you solve it you will get a 2a. Other this xi square will cut. So this is
Hmm.
your exact integral. Now let's do it with the Gauss quadrature. What you will write? You will write w1 phi 1 plus w2 phi 2, and let's go on to wn phi n. Now let's say what you have to do. You have to compare. You know that 2a should be equals to this. Now you 2a. So value of a plus y evaluated at psi is equal to 0. Huh. So let's use here one quadrature point. Since we are using one quadrature point, you will have to find mm, yeah, we have to do a coefficient matching here, and w1 phi 1 comparing 2 and 3. Okay, we'll compare this and this. This is a constant term phi 1. Okay, let's compute phi 1. Phi 1 will be uh, so when you use there are if when you are using a one point quadrature point to solve the integration, your xi is 0. When you are using a 3 point quadrature point, your xi is minus of some minus of some quantity, plus minus p and 0. You have to take one here, one left of it 0, one right of it, and a 0 point. So when you put this since you are using 1 point quadrature point in this, you will put phi 0 you have to calculate, which will get a. So you will get here w1 a as phi 1. So when you compare this, you will get w1 is equal to 2. I messed up little bit, but did you get how I got the w1 as 2? Did you get how I got w1 as 2?
Yes, that I understood,
Huh.
but I didn't understood that why where this xi equals to 0
So
and
these are the
plus minus
sampling
p.
points you have to take. So it is defined that The sampling points are also calculated. Uh, so the property of sampling points, I tell you, it should be symmetric with respect to
Mm-hmm.
xi is equal to 0. So if you are using a one sample point, xi will be 0. If you are
Okay.
using a two sample points, xi will be something plus minus p and 0. If you are using three sample points, no, if you are using a 3 point sample point, it will be plus minus p and 0. If you are using a two sample points, then xi will be plus p and minus p. Okay?
Okay.
Okay. Then this p is also computed uh, on basis of how much you are using it. Let's say, let's calculate it for cubic polynomial, because we have done it for one sampling point that we know that xi is equal to 0. Let's do it for cubic polynomial. So let's say phi is a plus b xi plus c xi square plus d xi cube. So exact integration, when you'll do I exact from -1 to 1 phi d xi, you will get 2a plus 2 3c. Directly you can integrate and get this. Now let's say we require two sample point integration from Gauss quadrature. So our xi will be plus minus p. Okay. So let us and weights should be equal. So W1 is equal to W2. Let's say it is at W. So when you write the equation from integration form from this, you will write W1 phi 1 plus W2 phi 2, which will become W phi at minus p, W phi at plus p. Is it okay?
But my question was slightly different. This I got it, means how
Okay.
we are integrating it. This is all clear.
Okay.
But how this value of plus minus p and this value of w will I get?
I am calculating this only. So you have
Okay,
now you will compare this exact solution with this.
okay, fine.
So what you
Uh,
will get? You will get from this equation. From this equation, let's say this is 1 and let's say this is 2.
mhm.
So from 1, what you will get? Uh, phi of minus p will calculate a plus cp square. Okay, phi is a plus b xi plus c xi square plus d xi cube. Phi at minus p will be a minus b xi plus c xi c xi wait, it will be minus b p plus cp minus d p square. Okay, now
Yes.
minus b a plus cp square b is equal to t is equal to 0. Okay, okay, okay. In yours, this is okay. A plus cp square. I think I'm missing something in the notes. B is equal to 0, D is equal to 0. I of minus P. Okay, okay, okay. From 1, the solution is 2A plus 2 by 3C. So we can understand that in exact solution B is equal to 0 and D is equal to 0.
Hmm.
Okay. Now in phi, when we put it as minus p, we can use in this equation that phi of minus p will be, we have to put it in this main equation, a plus b xi plus c xi square plus d psi cube. Now this is 0, this is 0. So this will become a minus a plus cp square. Understood?
Yes.
Then phi p will be a plus cp square again.
Correct.
Now what we'll do, we have the value of this phi minus p also, phi plus p also. So our I will be, we'll substitute in this and we'll get 2w a plus cp square. See, we are writing, since they are same, so it will add up and we'll get 2w a plus cp square. Now
Hmm.
let's do 1 minus this third equation. This third equation. So it should come at to 0, because
Yes.
for a exact solution. So we have the correct equation as 2a plus, or we can write this as, anywhere we can write, so 2w a plus cp square minus of the correct solution, which is 2a minus 2 by 3 c equals to 0. So now 2aw minus 1. Now what we have w as unknown, we have p as unknown. So we require one more equation. 2aw minus 1 is 2cwp square minus c.
We can also compare the coefficients, no?
We can compare the coefficient in which equation?
It's A and A, P and C and C,
Uh,
the same
no,
equation.
same equation. Yes, we can. What we can do, we can write it as 2a w minus 1. Uh, we can rearrange it. 2 say wp square minus 1 by 3. Is this correct?
Yes.
We have just made it here and there. Now we have got, we can compare and we can get w minus 1 equals to 0 from this, and we can get
Hmm.
wp square minus 1 by 3 equals to 0.
Yes, this is
So
a
from
homogeneous kind of solution.
this is 1, and from this we'll get p as 1 minus 1 by root 3. So this is the way of getting the weights of the in the Gauss quadrature, also the Gauss points at which you have to
Hmm.
integrate it. Similarly, if you have to
Hmm.
do a integration in this, you have to choose 1, 2, 3, 4, 4 Gauss points. You have to get these values of this Gauss for quadrature point, and you have to see what it is, how it is, which points are there, so that you can solve it for your normal FEM problem. Is this clear now?
Hmm. Yes. Now, how exact is this? Means, to which degree will it be correctly
Now
representing the?
it will be taught by in the later class,
Hmm.
to which degree you have to go. It's also that reduced integration thing what you are telling about. Will you have to do a full integration or you have to do a reduced integration? That you will get in the later class. You will understand
Okay.
there better. So
Okay.
this is the just gist of what I thought you will be struggling with the Gauss quadrature. So Gauss quadrature is nothing but is just a new way of solving a numerical method, because in FEM problems, if you use these old methods like Simpson and trapezoidal, you won't get that much exact solution. Rather using this, so you have to use this and get the more better, maybe better results.
Okay.
Hmm. Anything else?
No, that's all from my side.
Yeah.
Okay, so thank you.
Thank you. No problem. I'll wait for 5 minutes. If anyone has a problem, can ask, or you can leave the class.
Yeah, thank you. I will
Thank you.
leave.